Hello my dear friends. In this video lecture we shall be discussing about the node analysis, but prior to going for the understanding of node analysis we must understand some fundamentals related to it. Okay, so let us discuss some fundamentals. Okay, now let me discuss about one circuit. Okay, so very simple circuit is there, one resistor is there, and one DC voltage is there, right? Okay, fine. So let us say this is nothing but having a 5 volt source, and let us say this resistor is of 10 ohm. Okay, how you use to find out the current? Okay, so by means of Ohm's law. Okay, Ohm's law is there. Fine. By means of Ohm's law, we can write V is equals to I, right? So the drop across particular resistor is nothing but the current flowing through it and its value, right? So definitely we can find out I by means of the value of voltage we know, right? We know this value of voltage and we know this value of resistor. Okay, so right now this value is nothing but 10. But remember that whenever we are going to check this, we used to find out what is the voltage at this terminal of the resistor and what is the voltage at this terminal of the resistor. Okay, so right now as it is connected to the ground, so this is nothing but simply 0. So whenever we are calculating this voltage or the drop across this particular 10 ohm resistor, remember that the drop is nothing but 5 minus 0. Okay, fine. So with respect to something we use to measure the drop, right? So with respect to ground, here the drop is measured. So we need to consider the two terminals of that particular resistor and we need to check out what are the values of voltages present across that two terminals. If the other value, let us say if it is there 1, we'll talk about this right in the next example, but right now it is 0. Okay, so it is connected to the ground, right? So this resistor is directly connected to the ground and in between 5 volt. Okay, so 5 volt and ground, in between that two voltages it has been connected, right? So therefore we can say that the voltage across that particular resistor is nothing but 5 and it is divided by that particular resistor, and because of that we shall be getting the value of current as 0.5 ampere. Is it fine? But in case, let us say another circuit. Okay, there is one resistor, I have one more voltage source over here which is having a value of voltage, let us say 2 volt. Over here there is a 1 voltage source as like that 5 volt, right? So it is nothing but, again let us say take this 5 volt as it is, let us take this 10 ohm resistor. Okay, now as usual the tendency of this current is going to oppose to the flow of this current. Okay, and the conventional flow of current because of this 5 volt is going to become like this. Okay, so let us say this is I1 and let us say this is I2. This I2 is because of the 2 volt source. Is that fine? So because of that, the resultant current that is flowing through this 10 ohm resistance is going to become the subtraction of these two currents, right? So let us tally this by means of again Ohm's law. Okay, so Ohm's law, again V is equals to IR, right? And I can be found out as V divided by R. Now remember that what is voltage at this point of this resistor? It is 5 volt, right? And what is the voltage at this point? It is nothing but 2 volt. So we need to take the potential difference between these two. Therefore, we can say that the drop across this particular resistor is nothing but, let us say, that particular difference between these two voltages. Okay, so therefore 5 minus 2 divided by that particular value of resistor. Okay, again recall the that concept that we had a discussion while discussing about your mesh analysis, right? So this minus of this battery is been connected to this minus of battery. Is that fine? So that's why 5 will be that 2 will be subtracted this from this 5. Okay, and remember that if this voltage is let us say reversely connected, then definitely this is going to get added. Okay, right? So we'll discuss that as well, fine. But right now remember that 5 is connected and 2 is also connected, but they are in series subtractive manner. Okay, so they will work as series subtractive. Okay, so because of that 3 divided by 10 is the value of current, that is nothing but 0.3 ampere. So remember that whenever we are connecting two different voltages in a two different fashion, then definitely the value of current, previously it was having value as 0.5 and now it has reduced to 0.3. So it is all because of the opposition provided by this 2 volt source, that is nothing but I2. Okay, and because of that this value of current has been reduced from zero point 0.5 to 0.3. Okay, let us take one more example in which we have applied this voltage in a reverse manner. Is that fine? Okay, so let us take that. Let me redraw with a different color. Fine. Now identify the change, right? So this is 5 volt, this is 10 volt, 10 ohm, sorry, as it is. Let us say this is 2 volt as it is, minus, plus, minus, plus, right? Now what is going to happen with this? Now this minus of this battery is connected to the plus of this battery, right? So is it a series additive? Yes, it is. So therefore remember that again I is nothing but V divided by R, right? Now focus on this. This is having a 5 volt and this is having a minus 2 volt, right? Minus 2 volt. So minus of minus is going to become plus, definitely. So 5 minus of minus 2 volt, right? Because the minus terminal is connected over here to this particular resistor and divided by 10. So because of that, now it is going to become 5 plus 2, that is nothing but 7 divided by 10, and because of that this is going to have the value as 0.7 ampere. Okay, so depends on the polarity of the battery that we have connected over here and over here, the value of current is going to change because of this series additive and series the subtractive type of connections of the battery. Is that fine? So I wanted to discuss this one, right? So we need to understand, definitely we have to check out the voltages present at two different terminals of the particular resistor. Okay, so we need to check out the voltage present. This is nothing but one terminal of the resistor, right? This is nothing but one terminal of the resistor and another terminal of the resistor is connected over here. So we must check out what are the voltages present at these 2 points, okay, by taking their difference. Okay, remember that potential difference is nothing but voltage. Okay, potential difference means voltage, right? So difference we must take. Okay, so voltage over here is nothing but 5 volt and voltage over here is nothing but minus 2 volt. So we have taken a difference between them, right? So we have taken the difference between them, isn't it? And because of that it has become plus 7, and because of that the current of flowing through that particular 10 ohm, it is going to become this current is also flowing in this direction and this current is also going to flow in this direction. So this total current is going to increase, right? And it has been improved over here, or we have seen it, or we have found out by means of math, or we have proved it in a mathematical manner. Is that fine? Okay, so this I wanted to discuss first. Now let me discuss a very fundamental concept related to the KCL. Okay, I hope you are very familiar with the KCL. I know whenever I am going to ask what is KCL, you are going to say that yes, it's a Kirchhoff's current law. We know the long form of this KCL, isn't it? But ultimately, what we must know how to apply KCL, right? So let us consider that there is one simple circuit. Let me take this simple circuit so that you can understand it, right? We have already taken this circuit while discussing your current division rule. Okay, fine. But still, this kind of circuit we will take and will discuss about this. Okay, now this is nothing but treated as a junction. Okay, let me take another color. So this is nothing but junction. So whenever one or two, more than two connections are there, or more than one connections are there, then definitely it is called as a junction, right? Okay, so right now this 5 ampere is coming up to this point, okay, and then it is going to get splitted in these two branches, right? Let us say this is I1 and this is I2. Okay, now as these two resistors having same values, so because of that we know that the current always selects or chooses minimum resistance path, but right now both the resistors are having same values, so the current is going to get divided in a half manner. Okay, so 2.5 ampere current is going to flow from this 10 ohm resistor, and 2.5 ampere current is going to flow from this 10 ohm resistor. You can check it by means of a current division rule. Okay, is that fine? I'm not going to discuss right now that. Fine. And the statement of this KCL is what? The algebraic sum of all the currents incident on a junction is equals to 0, or in other manner, or in other words, sum of incoming current is equals to sum of outgoing current, that you know very well. Okay, right? So which are the incoming current in this circuit diagram? In this circuit diagram, the 5 ampere is the only current which is entering into this junction. Okay, so incoming current is 5 ampere. What are the, which are two current that are leaving from that junction? Those are nothing but I1, and we need to take their addition, that is sum. Okay, so I1 plus I2, isn't it? So 5 is equals to what is the value of I1? Is it 2.5 ampere? Yes, it is. Similarly, for I2 also there is a 2.5 ampere current. Okay, so whether it is satisfying this condition, so we can say that this is satisfying the KCL law, right? Great. So remember that these two fundamental steps I need to discuss with you before going for the node analysis. Okay. So now let us discuss the node analysis. Fine. So let us discuss node analysis. Okay, for DC circuits right now we are going to discuss, first understand the easy circuits and then we'll go for the AC circuits, right? So for DC circuits we are going to discuss it. Is that fine? Okay, before going for the node analysis, why we have gone for mesh analysis, that we need to discuss. Okay, and why we are going for node analysis, that also we need to understand. Okay, fine. So in case of mesh analysis, we have used KVL. Sorry, in case of node analysis, mesh analysis, we have used Kirchhoff's voltage law, and in case of node analysis, we are going to use KCL. Mesh analysis, we have used KVL. For node analysis, we are going to use KCL. So mesh is nothing but simply application of KVL, and node analysis is nothing but simply application of KCL, Kirchhoff's current law. Right? Great. When we are going to use mesh analysis? When there is a need to find out loop currents. So in case of finding out the loop current, we used method, method and purpose. Okay, what is the purpose? To find out loop current, and here to find out node voltages. To obtain node voltage and to obtain node current. Sorry, loop current. Okay. So mesh analysis. In mesh analysis, what is the method? Method is nothing but a KVL. We are going to apply KVL to different loops, and then by means of solving the simultaneous equations, we used to find out the loop currents. Right? Okay. So purpose is what? To find out the loop current present into different loops. Right? Node analysis, it uses method of Kirchhoff's current law, and why we are using this? The purpose for going for the node analysis is nothing but what? To find out the node voltages. Is that fine? So that is the basic difference between mesh analysis and node analysis, right? Before understanding any kind of concept, we must know why we are studying this concept, right? So for that purpose, I need to clear out this particular fundamental related to the mesh and node analysis, and then we can go for practically example based on this and how we can apply node analysis to the different circuits that we need to discuss after this. Okay, so let us discuss it. Fine. Okay, now let us again write node analysis. Fine. Okay, now let us take a very simple circuit for this node analysis. So directly we are going to understand how to apply node analysis with the help of one example, right? So we are not going to understand the theory related to it. Fine. So let us take the circuit diagram. Okay, so this is nothing but a current source, right? So remember that whenever there is a circle and into that circle there is an arrow, this represents the current source, right? Okay. And the arrow indicates its direction, in which direction the current is flowing, right? So please remember this thing. Great. Okay, so this is nothing but my circuit. Fine. Okay, so how many nodes are there? So this is one node. Sorry. This is my first node and this is another node, right? Where two or more connections are there, right? Okay, fine. So let us call this as node number 1 and the voltage at this particular node 1 is V1. Let us say this is nothing but node number 2 and the voltage at this particular node is V2, right? This current 5 ampere is going to enter up to this point. Fine. So up to node 1 this current is going to enter and then it may have the division of the current. Am I right? Fine. So let us call this is nothing but your I1 and this is nothing but your I2, right? And this I2 will come up to this point as well, right? So this is nothing but your I2. Now as there is a voltage source, so let us say that this current is going to flow in this direction. Okay, so let us say this is nothing but my current because of this 10 volt source. Okay, so I10 is nothing but a current because of the 10 volt source and let us say this direction as I3. Okay, fine. Now remember, let us apply current division. Okay, before going for the current division, remember that current always flows from the positive terminal or higher potential, high voltage, higher potential to low voltage. Okay, so remember that as this current I2 is flowing from one node junction 1 to node 2, right, to junction 2. Therefore, can we say that the current voltage at this particular point is larger as compared to V2? Then and then only this current is going to flow from this point to the V2, right? Similarly, in other case, I10. So can I say that this 10 volt source is definitely larger than the V2? Yes, it is. Then and then only this I10 can flow up to that particular V2 terminal, okay, or V2 voltage. Is that fine? So remember that this is a very basic fundamental that you know very well, right? But still I need to clarify that. Okay, so let us apply KCL at applying KCL at node number 1. Let us say that is V1. Is that fine? Okay, so we know that KCL, what is KCL? KCL is nothing but sum of incoming current is equals to sum of outgoing current. Okay, now concentrate on this V1 term. Okay, over here V1 junction. Which are the incoming currents? Only 5 ampere is the incoming current, isn't it? Which are the two outgoing currents? I1 and I2, and their summation we have to take, that is addition, isn't it? Fine. Now a very important fundamental. Okay, so for that purpose I have gone for the fundamental. This is nothing but your ground potential. Yes, this is nothing but the ground potential, isn't it? Right. Okay, so we had a discussion about how the current flowing through the particular resistor can be calculated, right? Okay, so same principle we are going to apply over here. 5 ampere current is as it is coming up to that particular point, right? How to find out the current I1? Okay, so current I1 can be found out. Which are the two terminals of this resistor? Over here it is there, and the corresponding voltage at this point is nothing but what? V1. And what is the corresponding voltage at this particular second terminal of this 10 ohm resistor? It is 0, right? So V1 minus 0, can I write it? Yes, I can write it definitely. Okay, so V1 minus 0 divided by 10, that will be giving me the value of the current which is flowing from the 10 ohm resistor, right? Okay, now similarly the I2, how we can find out I2? Now which are the two voltages will be coming into the picture? So V1 and V2, right? Because these two voltages are there which are connected between, or which are connected to these two terminals of that particular resistor 3 ohm, right? So the 3 ohm resistor is having two potentials as V1 and V2, but consider the direction of the current. The direction of the current is going to flow from V1 to V2. So whether we need to take V2 minus V1 or V1 minus V2, right? V1 is larger, because if the V1 is larger, then and then only the direction is going to flow from left to right. Otherwise it could have been right to left, isn't it? So therefore V1 is larger minus V2. We don't know what is the polarity of that particular V2, so that's why we need to take it minus, right? If it is negative in manner, then definitely it will the answer of V2 will come in terms of minus. Don't bother about it. Okay, so just consider that V1 minus V2 is there. Okay, fine, and divided by how much? Divided by 3. Okay, now simplify this equation. So 5 is equals to V1 by 10 plus V1 minus V2 divided by 3. Okay, we have simply neglected 0, right? Okay, now make the denominator common. Okay, so by means of LCM, make the denominator common and do the cross multiplication, right? So 3V1 plus 10V1. So let us do the cross multiplication of the terms. Okay, so that we can make the denominator common. Okay, so 10V1 minus 10V2 divided by 30. Am I right? So divided by 30, isn't it? 5. Okay, so whenever we are going to take this 30 to the left hand side, it is going to become multiplied with 5. So 5 into 30 is going to become 150, right? Is equals to 3V1. Okay, 3 plus 10, how much it will be? It is 10V1. Sorry, 10 plus 3, it is going to become 13V1 minus 10V2. So this is nothing but the equation that we have got after applying KCL at node 1. Is that fine? Okay, now let us apply KCL at node 2. Applying KCL at node 2. So which are the three currents that are incident on this particular node? That is nothing but I2, I3 and I10, right? So I2, what about I2? I2 is incoming current, as well as I10 is also a incoming current, right? So there are two incoming currents and one is the leaving current. Okay, so let us write it. Okay, let us write over here. Fine, so it will be easier to have a look of it. Okay, so incoming currents are which? I3 and I10, right? Sorry, not I3, it's I2. I2 plus I10 these are the incoming currents. Okay, so this is applying KCL at node V2. Is that fine? So therefore, sum of incoming current is nothing but what? Incoming currents are nothing but I2 and I10, and outgoing current is nothing but I3. Isn't it? We have already found out I2, right? We have already found out I2. Okay, so recall this I2. Is that fine? So you just take it as it is. Don't change it anyway. Okay, so as it is V1 minus V3 divided by 10, because the current is going to flow from V1 terminal, V1 voltage to V2 only, because this is considered as at higher potential than V2. Okay, you can assume any direction, no matter if whether you are going to consider this, but if you are taking the direction as let us say incoming direction for this junction, let us say V1, then definitely you have to take V2 minus V1, right? Then and then only that particular equation is going to get you, you will be getting a proper equation. Otherwise you'll be getting wrong equation, and you may face or you may get a wrong values. Is that fine? Okay. Plus what about I10? Again for I10, this 10 volt source is there, so 10 volt is larger as compared to V2. Then and then only the current I10 is going to flow from 10 volt to V2, right? So therefore 10 minus V2 divided by 1 ohm, right? Okay. And what about I3? I3 is nothing but simply V2 minus 0 divided by 5. So I am not going to write it 0. Is that fine? Okay, great. Now let us do again the simplification so that we can make the denominator common, right? So simply multiplying by 3 to this term, we'll be getting that. So V1 minus V2 plus 30 minus 3V2 divided by 3, okay, whole divided by 3 is equals to V2 by 5. Is that fine? Okay. Now again do some rearrangement. Fine. So V1 minus V2 minus 3V2. Let us give denominator separate to this 30 and 3. Okay, so let us give the denominator 3 to this one and 30 by 3. Okay, can I do this? Yes, definitely I can do it. Okay, because the denominators are same. Okay, fine. Now let us transfer this value to the right hand side and let us take this term to the left hand side. Is that fine? Okay, so V1 minus, sorry, what about this? This is V2. Okay, what about this then? It is going to get added, right? So minus 4V2 divided by 3. After taking this V2 divided by 5, it is going to become minus, and the 30 divided by 10 is going to become 10, and once I am going to transfer it to the right hand side, it is going to become minus, isn't it? I hope this thing is very clear. Okay, now again let us do the denominator common to do the simplification into this into this particular equation, right? So let us multiply by 5v1 in minus 4v2 minus 3v2 divided by 3 5s are 15, isn't it? Sorry, not 150, it is 15. Okay, and it is nothing but minus 10 as it is, right? Okay, so simplified 5v1 minus 5 4s are 20v2 minus 3v2 divided by, okay, instead of writing divided by, we just transfer it to the right hand side. It is going to get multiplied with the 10, so it is going to become minus 150, isn't it? Okay, so again simplifying this equation, so adding v2 terms. Okay, so let us add these two terms. 5v1 minus 23 v2 is equals to minus 150. Yes, so this is nothing but your equation number 2. Now simplifying this equation number 1 and equation number 2 to get v1 and v2, right? Okay, so let us multiply by 13. Okay, the simplest way is what? Multiply by this factor to this equation number 2 and multiplying by this factor to equation number 1. we can make the v1 terms common and then we can cancel out the terms. Okay, so let us write it over here, multiplying by, okay, let me take different color, multiplying by 5 to equation number 1, we get, okay, so 750 is equals to 65 v1 minus 50 v2, isn't it? So this is nothing but the equation after multiplying by 5 to equation number 1. Let us mark this as equation number 3. Fine. Now multiplying by 13 to equation 2. Is that fine? So let us do it. So let me write it as it is like this, 150 into 13, how much it will be? Let me calculate it. Minus 150 into 13, it is coming as 1950. 1950 is equals to, so 15 fives are, sorry, 13 fives are 65 itself. So 65 v1 minus 23 into 13, it is coming as 219. So 299, yes, it is 299 v2. Let us mark this as equation number 4. Okay, fine. Now let us subtract the equation number 3 from this equation number 4. Okay, so subtracting equation number 3 from equation number 4, right? Okay, so let me write it as it is. I'm going to write equation number 3. Okay, and we are going to subtract it, right? So minus is going to become over here, minus is over here, and this is going to minus is going to become plus over here, right? Okay, so this minus is going to get added, isn't it? So 19, okay, let me calculate that. Minus 1950 minus 750, it is coming as minus 2700. So minus 2700. So this is going to get cancelled out. So 0 v1 minus 249 v2. Okay, so from this we are going to calculate v2. Therefore minus 2700 is equals to minus 249. So we can cancel out minus terms. Therefore 2700 divided by 249 is equals to v2. Therefore let me calculate it. 249, and it is coming as, v2 is coming as 10.84. so v2 is coming as 10.84 volts. So this is the value of voltage v2. Is that fine? Okay, now let us put this value of v2. Putting value of v2 equals to 10.84 in equation 3. We get, so let us write it. Equation number 3 is nothing but 750 is equals to 65 v1 minus 50 v2. Okay, so 750 is equals to 65 v1 minus 50 into 10.84. Okay, so let me calculate 65 v1 minus 10.84 into 50. So take 50 into 10.84. It is coming as 542. So 542 is the value. Okay, fine. Now let us take this 542 to the left hand side. So it is going to become 750 plus 542 is equals to 65 v1. Is that fine? Great. So let us add 750 into this 542. So it is becoming 1292, 1292. So 1292 is equals to 65 V1. Is that fine? Okay. Now let us finally calculate the value of V1. So V1 can be calculated as 1292 divided by 65 will be giving you the value of V1. So let us divide it by 65. So it is coming as 19.87. Therefore, the value of V1 is coming as 19.87 volts. So likewise, you can find out the values of V1 and V2 by simply applying node analysis to such kind of circuits. Okay. In the next lecture, we shall be discussing further circuit about node analysis. Okay. Fine. Thank you.
Hello my dear student friends, welcome you all to the next video lecture on node analysis. Okay, so already we have studied what is node analysis. Okay, so in previous lecture itself we have studied how to apply node analysis and how to find out the node voltages, right? So let us concentrate on the another kind of example in which we have multiple resistors and one voltage source and one current source is there, and it is now having three different equations, and ultimately we are going to use a Kram's rule for that. Is that right? Okay, so let us first, whenever you are going to apply node analysis, the very fundamental step that is nothing but is to assume the current directions. Okay, so let us assume the current directions as like this. Okay, so let us say this is I1, say this is I2, okay, so this is I3, and finally this is I4. Is that fine? So this I4 is come up to this point as it is, right? So therefore it is I4, right? This 5 ampere current is coming towards this particular junction, right? So how many junctions are there right now? 1, 2 and 3. So voltages at these voltage nodes will be termed as V1, V2 and V3 respectively. Is that fine? Okay. So 5 ampere is current coming towards node 2, right? Okay. This I3 is also coming towards this node 2, right? And let us assume that this current is leaving. Is that fine? So let us mark this as I5. Okay, fine. Now this is another node. Okay, so I5 is coming as it is. Let us say I6 and I7 are leaving currents. Okay, so this is the first step that we have done by marking the current directions. Okay, now let us apply KCL at node 1. Okay, fine. So where is node 1? This is the node 1, right? Okay, so let us apply node 1, KCL at node 1. So what is KCL? Sum of incoming current and sum of is equals to sum of outgoing current is equals to, right? So sum of outgoing current is equals to sum of incoming current. Sum of incoming currents. Okay, fine. So which are the outgoing currents? So all the currents which are there for this particular junction, let us say V1 node, over there all the currents are leaving, right? So therefore can I write it as I1 plus I2 plus I3 plus I4, and there is no incoming current, so can I write it as 0? Yes, it is. Okay, fine. Now concentrate over here. How to find out I1? I1 is the current which is flowing from V1 towards this 10 volt, right? So V1 is larger voltage as compared to the 10 volt source. So V1 minus 10. And what is the value of resistor? It is 10. So it is divided by 10. Right? Plus, how to find out I2? I2 is nothing but the current flowing through this 5 ohm resistor. Right? So V1 is the only voltage because this is nothing but ground potential, isn't it? So 5 minus 0. So we are V1 minus 0. So we are not going to write V1. Sorry, 0. So therefore V1 minus 0. We are not writing minus 0. So therefore V1 divided by 5. Is that fine? Great. What about I3? I3 is the current which is flowing from V1, okay, to V2, isn't it? So remember that I3 is the current which is flowing from node 1 to node 2. So therefore V1 is termed as at higher potential as compared to V2. So V1 minus V2 divided by how much? It is 3 ohm. Right? Plus, what about I4 now? Now from I3 is also flowing. Yes, I3 it is over here, right? It is I4, no? Sorry. So I3 is also flowing from V1 to V2. Okay, so that is also correct one. Okay. And what about I4? I4 is also flowing from V1 to V2, and this resistor is also having value as 3. So therefore, V1 minus V2 divided by 3 is equals to 0, right? Because there is no incoming current. Okay, now let us find out the LCM of this. So what can be the LCM? It will be 30, isn't it? So 30 will be LCM. Okay, so simply multiplying by 3 to this particular equation, okay, or to this particular term, then multiplying by 6 over here, so that I can make it 30 at the denominator, right? And if I'm going to multiply by 10 to this particular equation or to this particular term, then the denominator will be becoming 30, right? Similarly, 10 we should multiply to this term as well, right? Okay, so let us do this. So 3v1 minus 30 divided by 30 plus 6v1, 6 5s are 30, plus 10v1 minus v2 divided by 30 plus, sorry, this is also multiplied by 10, right? Okay, so let me rearrange it. Minus 10v2, okay, here also 10v1 minus 10v2 divided by 30. Yes, okay. Now let us take this term separately, okay, and rest of all other term we are going to add together because they are having same denominator, isn't it? So 3v1 plus 6v1 plus 10v1 minus 10v2, again 10v1 minus 10v2 divided by 30 minus 30 divided by 30, it is going to become 1, isn't it? So is equals to 0. Yes or no? Okay. Now let us rearrange the terms. Okay. Fine. Now pull up the terms of V1. How much it will be? 10 plus 10, it is 20. 20 plus 6, 26 plus 3, 29. So is it coming as 29 V1? Is it right? 3, 6, 10, 10. Only these 4 terms are there, right? So 10 plus 10, 20, 20 plus 9, it is 29, right? And minus 20 V2, isn't it? So this 10 V2 and this 10 V2 will be added together and their minus sign will be as it is. Okay, divided by 30. Now let us bring this minus 1. Let us bring this minus 1 to the right hand side, so it is going to become plus 1, isn't it? So 1, right? Okay, now 29 V1 minus 20 V2 is equals to 30. So this results your equation number 1. So this is giving you equation number 1, right? Fine. So remember this one. Okay, now let us applying KCL at node 2. Okay, so let us consider the circuit diagram again. Okay, so over here, now focus over here. Okay, which are the incoming currents? Incoming currents are I4, then this 5 ampere current is there, and this I3. Okay, and only one I5 is leaving current, right? So what can be your equation? Sum of incoming is equals to sum of outgoing. Incoming means I4 plus I3 plus 5 is equals to I5, right? So let us write that. I3 plus I4 plus 5 ampere is equals to current I5, right? Great. So we have already found out I3 and I4, isn't it? I3 and I4 was over here. So I3 and I4 we have already used. Okay. So this was your I3, right? And this is I4, right? So we can directly use it. Is that fine? Okay. So let us use it. V1 minus V2 divided by 3, right? Okay. So let us write it. V1 minus V2 divided by 3 plus similarly V1 minus V2 divided by 3 plus 5, it will be as it is. Okay, so let us take this plus 5 to the left. Okay, let it be as it is right now. Okay, how to find out I5? Now let us focus on how to find out I5. I5 is the current which is flowing from voltage V2 to V3. Therefore V2 minus V3 divided by 2 ohm is the resistor, right? So V2 minus V3 divided by 2 ohm, right? So this is nothing but your 2 ohm resistor. Okay, the current is flowing from V2 towards V3, right? So V2 minus V3 divided by 2 ohm is the value of resistor. So it is going to give you value of current, right? V2 minus V3 divided by 2 ohm. Okay. Now let us rearrange this equation. Let us take this term to the left hand side and let us transfer this 5 to the right hand side. Okay. V1 minus V2 plus V1 minus V2, because their denominators are same, so I can add it, minus into bracket V2 minus V3 divided by 2 is equals to minus 5. Is that fine? Great. Therefore, now let us again do the denominator same. Okay, great. So before to that, we will first simplify this one. Okay, so twice V1 plus, sorry, minus twice V2. So we have added V1 terms and V2 terms. Okay, fine. Divided by 3 as it is. Now let us write plus over here and let us multiply by minus inside this bracket. So it is going to become V3 minus V2 divided by 2. Am I right? Yes. So after multiplying by minus to this bracket, it is going to become minus V3, it is going to become plus V3, and minus plus V2, it is going to become a minus V2, right? Okay. Now let us do cross multiplication to make denominators common. Okay, so we are going to multiply by 2 to this twice v1 minus twice v2, and we are going to multiply by 3 to this v3 minus v2, and therefore the denominator will have 3 into 2 is equals to minus 5. Yes. Okay, so 4v1 minus 4v2 plus 3v3 minus 3v2. Okay, let us transfer this 3 into 2 over here. So minus 5 into 6. Is that fine? Great. So let us simplify again. 4v1. Now club the terms of v2. How much it will be? It will be minus 7 v2 plus 3 v3 is equals to minus 30. Yes, 5 6 are 30. Okay, so this is nothing but your equation number 2. Is that fine? Great. Now let us apply KCL at node 3. We get. Okay, so let us again concentrate on the circuit diagram. Okay, now I5 plus I6, no sorry, I5 is equals to I6 plus I7, because I5 is incoming current and I6 and I7 are outgoing currents, right? So let us write it. Now you already found out I5. Okay, so over here I5 is over here, right? Okay. I5 is equals to I6 plus I7. What is I5? It is V2 minus V3 divided by 2. Already we have calculated it, right? In a previous itself. In a previous step itself. Okay, let us find out what is I6 and I7. Fine? Great. What is I6? How to find out I6? I6 is nothing but V3 divided by 1 is I6, and similarly this is the voltage, this is also V3 itself, isn't it? So V3 divided by 6, I will be getting I7, right? Okay, so let us write I6 as V3 by 1 and I7 as V3 divided by 6. V3 divided by 1 plus V3 divided by 6 ohms. Right? Is it fine? Let us check it out once again. Yes, it is 6 ohm, right? Okay, so let us write now. Let us do the rearrangement and let us find out the equation for that. Okay, let us bring all the terms to the left hand side. Okay, so V2 minus V3 divided by 2 minus V1 by V3 divided by 1, or let us say it is V3 itself, minus V3 divided by 6 is equals to 0. Okay, now what is the LCM of this? Let us say 6. Okay, so 6 is already over here. Let us multiply by 3 to this term and 3 to the numerator term as well. Okay, let us multiply and divide by 6. Okay, so let us do this. 3v2 minus 3v3 minus 6v3 minus v3 divided by 6. Okay, now the equation will have 3v2. Now add the v3 terms. Okay, so 6 plus 4, it is coming as minus 10 v3. Am I right? Okay, so 3 plus 1 is 4 and this 6 is becoming 10, right? And once we are going to transfer this 6 to the right hand side it will be getting multiplied with 0, so therefore it is going to become 0, right? So this is nothing but equation number third. Is that fine? Okay, so now uh, either we can simplify this equation number third so that we can replace value of v2 wherever there is v2 in equation number, let us say 1 and 2, or else we can directly go for the Cramer's rule. We'll simply go for simplification of this equation. So 3v2 is equals to 10v3. Is that fine? And therefore v2 is equals to 10 by 3 v3. So wherever there is a v2 in equation number 1 and 2, we are going to put it as this term and then we are going to simplify it. Okay. So let us check out whether v3 is there in equation number 1. No, it will not be there, right? So in equation number 1 there is no, yes, v2, we are going to replace v2, no? So instead of doing this, let us simply convert that v3 in terms of v2. Okay, so instead of doing this, let us convert that v3 in terms of v2. Okay, so that will be easier, isn't it? So it will reduce our computation time, right? Okay. So over here v3 will be what? 10 is going to get divided, so 3 v2 by 10, isn't it? So therefore it will be 0.3 v2. Yes, so wherever there is a v3 we are going to replace it by 0.3 v2. So putting this value in equation number, let us say let us mark this equation number as equation number 4. Okay, now putting v3 is equals to 0.3 v2 in equation number 2. Okay, so let us check out what is that equation number 2. So equation number 2 was consisting of 4v1 minus 7v2 plus 3v3 is equals to minus 30. Okay, 4v1, okay, 4v1 minus 7v2 plus 3v3. Four v1 minus 7v2 plus 4v3. Is it right? Let us check it out. Sorry, 3v3. Okay, is equals to minus 30. 3v3 is equals to minus 30. Is that fine? So let us put this value as 0.3 v2. Okay, so 4v1 minus 7v2 plus 3 into 0.3 v2 is equals to minus 30. Is that fine? Great. So let us simplify it. 4v1 minus 7v2, 3 into 0.3, it will be becoming 0.9, I think. So 3 into 0.3, it is 0.9. Okay, so 0.9 plus 0.9 v2 is equals to minus 30. Okay, so now let us add these two. Okay, so definitely the minus 7 is there, so from that 7 9 will be subtracted, isn't it? So 7 minus 0.9, it is coming as 6.1. Okay, so the modified equation number 2 is like this: 4v1 minus 6.1 v2 is equals to minus 30. Okay, so let us say this is equation number 4, and now let us recall that equation number 1. Okay, so this is your equation number 1, right? Okay, wait a minute. Okay, so let us mark this as equation number 5. Okay, and we know that the equation number 1 is 29v1 minus 20v2 is equals to 30. So this is your equation number 1. Now we are going to simplify these two simultaneous equations. Okay, so let us multiply by 29 to this equation number 5, and let us multiply by 4 to this equation number 1, so that we can make these two terms, v1 term, common, and then we can subtract the resulted equations. Okay, so multiplying by, let us say, 29 to equation number 5, let us multiply them. So 4 into 29, 4 into 29, it is coming as 116, 116 v1 minus 6.1 into 29, 176.9 v2 is equals to minus 30 into 29. 30 into 29 is minus 870. Okay, so let us say this is now equation number 6. Now let us multiply by equation, multiply by 4 to equation number 1. Okay, so 116 will be over here as it is, minus 20 into 4 is 80, 80 v2 is equals to 120. Okay, fine. So let us say this is equation number 7. Let us check it. So 29 into 4, is it coming as 116? Yes, it is coming. 24s are, yes, 80. Okay, and last 30 into 4, it is coming as 120, isn't it? Okay, so now let us subtract equation number 7 from equation number 6. Okay, so subtracting will result like this. It is going to get cancelled out, right? So 80 is going to get subtracted from 176, minus 176.9 plus 80. It is coming as minus 96.9 v2 is equals to, now 870 and 120. It is coming as minus 990. Okay, minus minus, let us now calculate v2. Minus 990 divided by minus of 96.9. Okay, so let us calculate it. Divided by 96. It is coming as 10 point. So v2 is coming as 10.21 volts. Okay, so this is the value of v2 that we are getting. Okay, now recall the equation number 4. Okay, so let us recall equation number 4. Remember 10.21. Okay, now recall over here. Okay, so in this equation number 4. Okay, so now we are going to put v2 is equals to 10.21, right? So 10.21 we are going to put it in this equation number 4. So putting v2 is equals to 10.21 in equation number 4. We get V3 is equals to 0.3 into 10.21. So therefore V3 is equals to 10.21 into 3, sorry 0.3. It is coming as 3.063 volts. Okay, and let us find out now finally V2, sorry V1. Okay, now putting V2 is equals to 10.21 in equation 1, we get, so 29 V1 minus 20 into 10.21 is equals to 30, right? So 29 V1 minus 20 into 10.21 is coming as minus 204.2 is equals to 30. Now let us transfer this to the right hand side. So 29 V1 is equals to 204.2 plus 30, right? So it is giving you 29 V1 is equals to 234.2. Okay, so let us finally calculate V1. Therefore V1 is coming as 234.2 divided by 29. 234.2 divided by 29. So it is coming as 8.07. Is that fine? Okay, very good.